name is Larisa Thorne. I am representing the KATRIN and Project8 collaborations here, and I'd like to give you a bit of a picture of the improvements to neutrino mass limits in the past few years. So let's start with a brief outline of my talk. I'll give a bit of a primer on neutrino physics first because I want to bring everyone up to speed. Then I'll dive right in. I'll start with my talk with an overview of the KATRIN experiment. This is the one I've spent the most time on, and again, the subject of my PhD. I'll talk a little bit about the recent measurements that we've done and some of the neutrino mass analysis with a custom analysis framework called CMKAT. All right, so I'll talk mostly about KATRIN since that's really where most of my expertise lies. And then I'll move on to talk a bit more about Project8. I'll give you an overview of what this experiment is and does, some very first results from it because it's in a different phase of its experimental lifetime as KATRIN is. And I'll sort of end the talk with a bit of an overview of the atomic test stand that we have at the University of Mainz, where I started as a postdoc recently. And yeah, so I'll show some first results from that. All right, let's get started. So to give a bit of a primer on neutrino physics, I'd like to start with a historical note. So around the 1930s, we found that beta decay shows a continuous spectrum, and this is significant because it means that it violated the conservation of energy at the time. For perspective, there were two other kinds of decays at the time, alpha and gamma decay. Those were typical two-body decays, and so there'd be a very sharp line if you measured the energies in these reactions, and that would represent the difference between the initial and final state energies. But beta decay was different. It showed a continuous spectrum, and that sort of caused a bit of a big fuss. Why are we seeing a continuous spectrum when we only expected a line in energy? And one of the solutions was proposed by Pauli. His solution to the problem was to say, aha, there's a third unseen partner in this decay. And so he suggested that we add a neutrino. There was a bit of a problem with this because it was going to be very light and it would be very difficult to detect. And so there was a bit of dismay at this possible solution. So fast forward about 20 more years to the 1950s, we see some first experimental detection of the neutrinos with the Cohen-Rines experiment shown here on the right. And this was very exciting because we finally have some proof that this particle does exist and take part in beta decay. This continued on for a little while until there was another interesting experiment, which is the Homestake experiment. And their purpose was to measure neutrinos that came from the sun, so from our very sun. And they wanted to measure the neutrino solar flux. And they were prepared to compare the experimental results with the theoretical predictions of the time. Problem was, when you actually evaluated this, there was a mismatch between the experimental solar neutrino flux and what was predicted by the theory. So that indicated that there was something else going on that we could not yet explain in our model. And so it took quite a few decades to approach this problem and to find a good solution. But finally, in the late 90s and early 2000s, we have a definite resolution to this discrepancy. And this came in the form of the statement, neutrinos experience flavor change in flight. And this sounds a little bit nebulous, but I will continue on and enlighten you. So what do I mean by flavor change? So neutrinos undergo oscillation in flight. They are born in a particular flavor eigenstate, which is associated with the partner in decay. For example, if we have, here I have a neutron turning into a proton plus electron. The partner in decay, the lepton, is the electron. So the flavor state that we are expecting here is an electron flavor state neutrino. But during flight, they oscillate into mass eigenstates, and there's a mixing between these two as defined by this p-MNS mixing matrix. If you have a bit of a stronger background in nuclear physics, you can think of this p-MNS matrix as analogous to the CKM matrix, talking about mixing between, I think it's quarks or gluons. Anyway, so this constitutes the flavor changing behavior of the neutrinos in flight. And this was explaining why we are seeing less than we calculated in the experiment. So besides this flavor oscillation, which is a pretty big feature of neutrino physics, there's also some more interesting features to the neutrino sector. I've highlighted 3 here that I find the most interesting. There'll be mass ordering, the type, and the absolute mass scale. What do I mean by mass ordering? Normal versus inverted simply means how would we organize the neutrinos in order of greatest mass to least mass of these 3 eigenstates. The type simply refers to whether they're Majorana or Dirac. Are they their own antiparticle? We don't know. I won't go into too much more detail with this ordering and this type because the KATRIN experiment is really designed to answer this 3rd question, which is, what is the absolute mass scale? We have no idea. And the solution to that is to try to do a direct measurement of the neutrino mass. So, branching out from this, we have neutrino mass physics. How might we go about measuring the mass of the neutrino? There's 4 different approaches you can imagine taking. The first comes from cosmology. You can know something about the cosmic microwave background, sort of studying the local anisotropies. You can also do a supernova time of flight measurement. So there's a dispersion in the time of arrival of neutrinos coming from supernova, and you can extrapolate some sort of mass from that. You can also search for neutrinoless double beta decay. So this is a decay process that has not yet been seen, but is technically not disallowed. And if you are successful in finding a few events like this, you can also learn something about the neutrino mass. The 4th method is I broadly call kinematic methods. This mainly involves looking at things like the beta decay spectrum of various isotopes. So this 4th method will be my focus. There are a few even more specific methods to taking advantage of this beta decay. The first one is through electromagnetic collimation, and this is what the KATRIN experiment uses. And another one is a frequency-based measurement, completely different, but same start principles, and this is the principle behind Project 8. Right, so now I've maybe built a little bit of a picture of what the state of neutrino physics is and how we might go about measuring neutrino mass. And let's start with the KATRIN experiment. Right, so KATRIN in a nutshell. Again, I've mentioned that the goal of KATRIN is a precision absolute effective neutrino mass measurement. And here maybe I'll do a quick just excursion to say, whenever I mention neutrino mass, in the KATRIN sense, what we are actually measuring is an effective neutrino mass, which is the incoherent sum, which is weighted by these matrix elements of the mass eigenstate values. So M1, M2, and M3. We're very creative as physicists in naming new things. So when I say neutrino mass, this is what I mean. It's an effective mass. All right, but the KATRIN experiment has been designed to measure up to a sensitivity of 0.2 eV neutrinos, meaning if the neutrino is found, it can only be measured by the KATRIN experiment if it has a mass of 0.2 EV or more. And this is with a 90% confidence level. So the method for KATRIN experiment is to utilize an intense molecular tritium source, so T2, and it does this by high resolution integrating spectrometer with a resolution of about an electron volt. And the detection of what you're actually detecting with this experiment is electrons from beta decay, and those are found in the detector at the end. So you might, some of the more experienced folks in the audience might say, well, we've already seen this kind of experiment about 20, 30 years ago with the Mainz and Troitsky experiments. This is true. It used a very similar setup, but the KATRIN experiment is at least 10 times more sensitive than they are. And these experiments, neither of them were able to find the neutrino mass in their sensitivity range. So it's very important to continue to push the boundaries to increase your sensitivity and try to look in this new regime that's opened. What is the design principle behind it? So I mentioned before that we're looking at a tritium beta decay. So this is 3H turning into an isotope of helium plus an electron, and the neutrino flies out. The quantity that we're actually measuring with the experiment, again, is circled here. It's the electron. So we're building a beta decay electron spectrum as shown here in the left-hand plot. So this is the entire plot. This is the range of energies that you can expect to find of the beta decay electrons that come out of this decay, right? But how does that relate to the neutrino mass? If we look at the very end point of this spectrum, so let's zoom in here on this right side plot, if you had a neutrino that was had some amount of mass that was greater than 0, then you can expect that in a 3-body decay, the mass of the neutrino is going to take away a little bit from the maximum possible energy that the electron traveling out can have. So that means that as compared to a spectrum where the neutrino has no mass, the expected spectrum where the neutrino has some positive mass will be shifted over a little bit, so it'll take away from some of that maximum energy. And I do want to be a bit careful with my language here. The difference between a 0 neutrino mass beta decay spectrum and a positive neutrino mass beta decay spectrum is not a shift. It's not a shift, it's a shape change in the end. And this will become a bit more clear once I go over the parameters in my fitting model. Right, so just general information, you can model this tritium beta decay spectrum. It comes from Fermi's golden rule. This is a differential spectrum, and then you can start making various corrections depending on what might be needed for the particular experiment that you're looking at. And I'll go over those in a little bit more detail in a moment. And then for the sake of nuclear physics, I want to mention tritium is selected because its beta decay is super allowed. I believe that's because it makes the nuclear matrix elements here a little bit more straightforward. And yeah, other things are like it has a smaller, more appropriate half-life, and its energy, its endpoint energy is fairly low compared to other candidate isotopes that you could be using for this. So it's a really nice candidate for a beta decay spectrum. Right. So now that we've sort of outlined how we imagine the physics to go, we still need an experiment to measure this spectrum. So here is the entire KATRIN experiment in this CAD model in the middle. For sense of scale, from the left sides of this yellow item here, all the way to the right side is about 70 meters. I'm about as tall as this little gray cabinet here on the very right. So it is quite large when you look at it. And there's various aspects that are just really impressive from an engineering standpoint. And I guess even myself as a physicist, I'm very impressed by it all. So we take our tritium in its molecular form and we pump it into this blue section. This is the windowless gaseous tritium source section, WGTS. And we begin by allowing it to decay here. So we have now a bunch of helium isotopes. We have the electrons. Maybe we have a bit more tritium that hasn't decayed yet. And we want to begin to guide those downstream to the right side where our detector will be. But we also don't want to measure any helium. We don't want to measure any tritium. We really want to isolate the electrons. We want to get rid of everything else. So the point of this red section here is to guide and to filter out all of the stuff that is not an electron. The first part of that is the differential pumping section. And this will reduce the tritium flow, meaning you're going to get rid of all of the tritium that hasn't decayed. And it gets rid of some of the other stuff like the helium. And this is done by mechanical pumps because this is a sort of good regime to use those. Unfortunately, at some point you can't pump anymore, and so you need to be a bit more clever about how to reduce and get rid of all of the non-electron stuff. And that is the purpose of this second part of the red section. This is the cryogenic pumping section, and it uses an argon frost to capture all of the remaining tritium pieces. So at this point, we've reduced the tritium flow by about 12, 13 orders of magnitude, and now we can be quite sure that we're not getting any stuff that's not an electron into the rest of the experiment. Now we can begin filtering. And the part of this principle, again, is that KATRIN is an integrating spectrometer. So the spectrometer part will create a potential energy barrier that only allows electrons of energy greater than that barrier to pass. So when you're doing an integrating measurement, it will involve setting your filter at different potential values, and this allows you to create different collect counts at different settings. This will become clear once I show you a sample data set, but keep this in mind. So these spectrometers are intended to filter the electrons by energy. They'll also do things like guide things and make sure they're adiabatic. And this makes our results a lot more easy to interpret. And then finally, after we've filtered them all, of course, they all need to be detected. That is the purpose of the detector section at the very end. We have a small detector wafer. It's about this large, I think 12.5 centimeters in diameter, and it's segmented into 148 equi-area pixels. And the pixeling is only useful for systematic studies. There's no need to actually pixelate the thing. We're just counting electrons at different energy settings of the spectrometers. Yeah, so that's in general, you can say that's how it works. We're going to put in some tritium, we're going to guide it, we're going to filter out all the non-electrons, and then finally we're going to create a few measurement points and count at those measurement points. Don't think this will work as a GIF, so I'll go to this slide. This essentially shows what you would see if you were doing a KATRIN measurement now with a scan through a peak of a calibration line. I'm not going to show tritium right now for the moment because it's a little bit easier to understand the integrating measurement principle with when you're scanning through a line. So let's look at this green line right here. This is, in our case, a krypton line. This comes from krypton 83M. It has quite a few nice sort of monoenergetic lines that are about an EV wide, so in their natural width. And if we wanted to make an integrating measurement of this with our KATRIN spectrometer, we would set the potential of our spectrometers at different values here along the x-axis. So if you imagined putting the spectrometer at this potential, only electrons with greater energy would be able to pass through that spectrometer. And so you're getting a lot of counts, you're getting no counts because at this energy there aren't very many electrons. So if you scan upwards and allow some time to measure at each potential set point the amount of electrons, then you can start getting this differential spectrum here. And so you can see that the counts increase as you're passing through the line here. So you're seeing the greatest increase in counts when you pass right through the maximum of this peak. So this sort of demonstrates the principle of the integrating spectrometer. And this is important to keep in mind because whenever you see KATRIN data, you're seeing integrated tritium beta decay spectrum. You're not seeing the differential one. Right. So we've talked a little bit about how the measurement works. What have we done recently with KATRIN? There are a few recent measurement campaigns of interest. I'll start with the very first one that we had in October 2016. We call this First Light. This was the very first time that the KATRIN experiment was put together in its entirety. So the beamline, all 70 meters of it were put together. And we sent some electrons through. It's not very romantic. It's just an electron gun. We wanted to make sure it worked before we put in the tritium, which is radioactive and would contaminate everything. So make sure that it works before you put the radioactive stuff in it. So that worked out just fine. So we moved on to the next step, which is injecting krypton. Krypton, I've mentioned before, but not in detail. This is a calibration source. It has a set of very nice monoenergetic lines, so they're at pretty well-constrained energies, and so that makes for a really useful tool for measuring the effect of different things in your setup. So again, that was sort of done for calibration and characterization. Then in the summer of 2018, right after one of the international neutrino conferences that we have every 2 years among the neutrino physics community. We put in the first amount of tritium. It was a very small amount of tritium, but it was really exciting because a bunch of important people got to press buttons and that allowed it to go through the entire setup. And it was very exciting to watch the detector light up with its first tritium beta decay electrons. But we didn't stop there. Obviously, that was just for a very small test amount of tritium. So we started with our very first campaign here in spring 2019. KNM1, so KATRIN Neutrino Mass 1, again, we're very creative, was our first tritium measurement campaign. And we published some results from that. We set a new world best limit. I won't go over that because we already beat it. But we got on the cover of PRL, which was pretty exciting. This is one of the more famous pictures that you see when you Google KATRIN experiment. And then we kept going. We kept gathering more data because we need more statistics. So the KNM2 campaign followed in fall 2019. We've already published some results on that. More on that later. KNM3 followed, and so on and so forth. We're actually currently measuring right now. We're up to KNM6. And luckily, we were not very strongly impacted by COVID. I think we were only down for about 5 weeks because our cryogenic operators couldn't go over the border from France to Germany. So it was really a technicality. So yeah, there's a lot of data being gathered right now, and it's very exciting. All right, so let's move on to the fun stuff, in my opinion. I had the pleasure of doing an analysis on some of this very first tritium beta decay data. And as is the case with most larger collaborations, we have a few parallel efforts in analysis. The one I'm going to describe here is one that was designed in-house, so in our university between my advisor, Greg Franklin, and myself. We designed this entire framework to fit, to model and then to fit the neutrino mass data that comes from the tritium beta decay data. Some technical details, it was written in C++. I use min-wee, chi-squared minimization, all that fun stuff. Yeah, our sort of departure from the other fitting programs is that we were able to take advantage of some linear terms in the model to speed things up, and that was kind of exciting because in the end I did a fit in a few minutes that took the others a few days. So it's always exciting to be able to do clever little tricks to save yourself some time. Okay. But I wanted to point out two models. This package includes two models. Of course, tritium model, which is the data that we'll be analyzing to get the neutrino mass result, and the krypton model because it's also important to be able to fit the calibration data. So the tritium model, it's described very briefly here. The interesting thing is that to fit this tritium beta decay model, you need at least 4 parameters, only 4. Very impressive to me. The first one is the normalization, which can scale with the amount of activity that you have in your source. A linear background, so if you measure beyond the endpoint of the beta decay spectrum, normally you wouldn't see any background because you don't expect any electrons out there, but there will be some due to other processes that are not from your tritium source. So again, that's the background. The other two more interesting parameters now are the endpoint. So this is related to where the tritium beta decay spectrum goes to 0. And this m squared parameter, again, the effective neutrino mass squared. And this is a shaping parameter. Again, it's not a shifting of the spectrum, it's really the shape changing. Quickly, the krypton model also happens to have 4 parameters: a normalization, a background, a line position, and a natural line width. All right, so I will move on. So I put this slide here because I wanted to give you an idea of, generally speaking, what goes into this model. Of course, we already talked about the interesting part, which is the source. This is usually for the actual neutrino mass data set. This would be the tritium beta decay model, which I showed a few slides ago. It could also be interchanged for this easier krypton calibration line, which is just a void function. But because our experimental data is not just pure physics, it's actually seen through the lens of the KATRIN experiment. So you need to take into account what the response function is of your experiment. And so that's the role of this. A few important inputs to this include how many tritium molecules you have occupying your space. We call this the integrated column density. Also the transmission function, energy loss function, and the scattering probabilities, because of course there's going to be interactions in that section that's holding the gas. They're going to be hitting each other. And if you take the convolution then of this physics source and this response function from the experiment, you then get a model for the data that we actually gather at the detector. Okay, so I wanted to present two different analyses that can be done with current KATRIN data. I chose first to talk a little bit about krypton, because it turns out that not only is it good for calibration, it's also a good way to make estimates on inputs for your tritium model to make it better. So in this case, it was to help reduce a systematic that we had a bit of trouble with. And I'll also, of course, show you the tritium analysis. This was a big feature of my PhD, and it relates to the paper that we recently put out. So I've already showed you what the krypton line generally looks like if you're looking at an integrating measurement of it. So again, this shape is nothing new. It's you're scanning through a line here, and yeah, so you're scanning through a line. So in this case, we wanted to know a little bit more about the source conditions. We suspected that we had some sort of non-neutral plasma in our source chamber in the WGTS, and that was effectively smearing out what the electrons' starting energy were. And that's a bit of a problem, because you really want to know what kind of energy they start with, because that can significantly smear out your neutrino mass at the end. So you need to characterize what's happening in that source area so that you have a handle on what those initial starting energies are. So how do we do that? We injected both krypton and tritium at the same time into this source section, mainly so that the krypton could experience the same conditions as the tritium did. And so it was behaving in a way that we could say is analogous to just the tritium on its own. And the effect of this non-neutral plasma would have is a broadening effect. So it smears out the spectrum. If you look just at the krypton line scans, this would just spread out the peaks that we see. And if you can deduce how much spreading there is in the peak just for krypton scans, then you can take that value and you can plug it in then to your tritium analysis. And that was something that was very important for us in accounting for some systematics. So yeah, here's some fit parameters. I won't dwell too much on them. It was a good fit. Everyone was happy. Yeah, and then as I said, you can calculate how much extra spreading there is in that line beyond the natural line width. We got a few values here. This is shown for different settings in that source chamber area. There's an end cap on one side that we call the rear wall. Again, we're very creative as physicists with naming. And if you put them at different conditions, you can affect what the starting potentials look like in the source chamber. So we went around and checked different settings, applying different potential biases to this. Yeah, things like that. And so we found that we had an average smearing for a particular setting of about 48 millielectron volts on these particular source conditions. So yeah, that was just for a particular setting that was analogous to a lot of the rear wall settings that were used during the regular tritium running. So it was really important, or really easy to take that value and now plug it into your tritium analysis. I also wanted to point out that this isn't the value for all analyses. There are other factors at play, other conditions, what the column density is and such. So don't look at this and say this is true for all tritium beta decay measurements. So that's an example of one of the things you can do with just your krypton source. All All right, let's move on to the tritium fit. So on the left-hand side, you'll see a plot where the blue data points are actual measurements of the integrated spectrum. You'll see now why I showed you what the integrating spectrum looks like on the krypton. Honestly, the difference between an integrated and a differential tritium spectrum, they look really similar, especially at the endpoint, so it's very hard to tell the difference. Anyways, yeah, so this data set here represents about 317 runs. We had 27 full days, so this is 24-hour-long days worth of statistics. We did a few steps of blinding, which we consider to be very important because we want our colleagues' trust that we're not somehow biasing ourselves. So once we finally met all of those requirements, we unblinded and I fit the spectrum. I combined data in a particular way using binning. Just to make the fit much faster, otherwise you'd have 317 times more fit parameters. And if you can cleverly do that, then you can reduce the number of fit parameters to something very manageable. In this case, we decided to split up the detector into 4 regions that were radial so that we could take care of any unintended radial effects with the fit parameters. And we let the endpoint be free, the normalization and background, and we allowed the neutrino mass parameter to be shared by all of these regions. There's another parameter that relates to the amount of tritium atoms in the source, but I won't go over that at the moment. So there was the result of the fit. 28 electron volts squared for our effective mass squared. This is our best fit value for this particular data set. And you can use that to construct a confidence interval at 90% confidence level. And in this case, I used the statistical uncertainty from the actual data set, but I took the systematic uncertainties from the paper that I'll show you in a moment. It's a pretty good approximation. I couldn't, as a one-person development team, I couldn't do all the systematics on my own. It's a bit much. But the nice thing was that my results agreed with the parallel fitting efforts, and that's always a really good feeling when you turn the crank on your experiment and you get similar results as your friends do. So that was very nice. What else I want to say? Ah, yes, okay. So here are the final KATRIN results. This paper is on arXiv. This is the KNM2 data set that I mentioned before. Here I'll flash what our best fit result was and how you use this to construct a new upper limit. And this is really exciting because if you look at past experiments that have tried to measure the neutrino mass in this way, they've always gotten a negative m² value. And now for the first time it's positive, and that's a really great sign because that means we really have a pretty good grasp of our systematic uncertainties. And so it's a pretty big milestone, I would say. And then below, just quickly, we combined our results from KNM1 and KNM2 just to win some statistics, and you're able to bring down the upper limit even just a little bit further to 0.8 eV. So this is the new world best neutrino mass limit at 90% confidence level. And there's a plot here on the right, which is shown in the paper, a paper which is on its way to Nature Physics. Our reviewers are all giving us a thumbs up. So at some point soon, you'll see this result in Nature. All right, so that'll conclude my talk about KATRIN physics. Now I'm going to switch gears to Project 8. Okay, so remembering way back to the beginning of my presentation, I mentioned that this is one of the experiments which can be used to get the absolute neutrino mass, but it does this kinematic method in a different way. It does a frequency-based approach. And how does it do this? The measurement is of the cyclotron radiation from trapped beta electrons. So this technique has a new name, a fancy new name, CRESS, which is cyclotron radiation emission spectroscopy. It's fairly new. In fact, I think it's the first experiment of this kind. There's no predecessor experiments. And because it's so new, it's still sort of in a development phase. We have, however, shown proof of concept that it works. There's a demonstrator experiment that showed that, yes, it does work. Of course, our limits are terrible for that because it's only a demonstrator and it's very tiny, but we're continuing to work a little bit more on that with time. The thing I'd like to point out is that our goal sensitivity is 40 millielectron volts. So in the final stage of Project 8, we aim to have a 40 millielectron volt sensitivity. That's a lot better sensitivity than KATRIN has. So this could be considered a next generation experiment. And there's a few improvements along the way, which I will explain in a moment, which will get us down from the KATRIN best level to the Project 8 level of 40 millielectron volts. So this graphic describes basically how the measurement works. We have a magnetic trap. I think it's about a Tesla deep. And we aim to trap beta decay electrons inside of that long enough to see them radiate their cyclotron radiation. And we plan to read that out with little antennas. And because you can measure frequency with that, you can actually turn it into the corresponding kinetic energy that those beta electrons had. And of course, you know the story from there. Once you know the electron kinetic energies, you can make a differential spectrum. It's essentially the same part as KATRIN at that point. So the hard part is making these frequency measurements. All right, so here already I'm showing some first results from the Project 8 experiment. This is that differential spectrum I was discussing. You can convert those frequency measurements into kinetic energies of the electrons. So these are reconstructed energies, and you can get a nice spectrum out of it and fit it. And there are the results from that. Here are some quick numbers to look at. So it gave an endpoint here with quite large error bars. And neutrino mass limit of, well, you know, it's a lot bigger than what KATRIN has right now. But this was a demonstrator experiment, so it was nice to see that it works. I'd like to point out that they had super low background count rate, which is really impressive. In terms of systematic studies, those are still in progress for this. I believe that the scattering model is the biggest source of error right now, and they're still quite statistics limited because this was only about 80, 90 days of actual data. So there's still far to go, but it's still super encouraging because this is the first spectra that we're getting from this very new novel technique. Again, I mentioned that we're at the very beginning of our journey as an experiment. This is a sort of rough timeline of Project 8 experiment. We've done our demonstrator experiment. We've shown some results for the small scale results. Now we're sort of up to here, so 2021. We're busy building phase 3, which will be the next scale up in this experiment. And the final state, which was the one that has that best sensitivity, is going to be called phase 4. And one very important ingredient to achieving that absolutely great goal sensitivity is to use atomic tritium. Before, we've been only talking about molecular tritium, and that's fine. It works for the KATRIN experiment, and as I said, it has some great properties that are really useful for this kind of work. However, if you want to really decrease your systematics, you would want to switch from molecular to atomic tritium. Why is that? If you have molecular tritium, you have two tritium atoms together, and one of them does its beta decay. Some of that energy might actually go into a rotational state or a vibrational state or some other electronic excited state. And that's energy that you didn't account for in the rest of your model. And it sort of blurs things out. It's a bit difficult. We have a component of the KATRIN experiment which is very computationally oriented. They're our more theoretical branch, and they're trying to work on mapping out these distributions of the final states for that tritium T2 molecule. But it's very difficult, even though it's such a simple molecule. So we would really like to switch to atomic tritium, which doesn't have this problem of having some energy loss to vibrational and rotational and electronic excited states. So that is where some of your biggest and easiest wins could come from. How would you get that, though? The answer is to crack your molecular tritium to get atoms. And this is a nice example. This is actually commercially available. You have a cracker, you can take it, you can put it in your experiment and be done, right? Almost. It's still really difficult. You need to characterize your setup a lot because this tritium really likes to recombine and turn back into T2 or some other combination of tritium, like DT, which is deuterium atom and a tritium atom, or HT, hydrogen and tritium atom, and all these other things. So it can be quite annoying, and you have to be a little bit careful when you characterize your experiment so you can take that into account. You can kind of think of it as like an efficiency, right? Because you only have a certain amount of true tritium atoms staying in their atomic state and not recombining with something else. So what I'd like to show here is the test stand that we're developing at Mainz. On the left side, I've tried to show a CAD model because the right side, which is a photo, is a little bit busy, as it so happens to be in a lot of experimental labs covered in tinfoil and everything. But the idea is that this is the cracker up on the top. So on the left here, it's this piece, and this would be where we inject our gas, and it cracks into its atomic state, and then it goes through these two sections, and we can analyze it there using various kinds of mass spectrometers. In this case, though, we actually use hydrogen instead of tritium. This is slightly for bureaucratic and safety reasons. Tritium is tightly regulated, so we're going to work with hydrogen for the moment. A lot of the same principles transferred. You can use what you learned from your hydrogen setup for your tritium setup. We're currently communicating with the lab that supplies tritium to KATRIN to build a similar test stand and let them put the tritium through it. But we first need to make sure that the test stand actually works. And that's the point of my work at Mainz. So we're developing this test stand, we're characterizing it, and we're testing different configurations. And we have successfully demonstrated some hydrogen cracking. So this is some of the very first exciting results from our setup in Mainz. We see that we are successfully cracking some hydrogen. And let me walk you through the very short data analysis process for that. So if we inject some H2 through the top and turn on the cracker, if we give it more power, then a filament will heat up the gas flowing through, and it will begin to crack your molecular hydrogen. But it'll only do that at some point, because at some point, if your temperature isn't hot enough, then it will not crack. And conversely, if you don't have, you'll see more of it as you get to higher temperatures. So how do we get this plot? This is our data. If you look at the at the blue lines, this will be the power of the cracker. So this represents us stepwise heating up and waiting at a particular power setting for the cracker to crack all of the hydrogen that it has in there. And then the red line is the atomic signal. So this is what you get if you scan with the mass spectrometer over a mass number, so m/z of 1. And you can count the number of hits in the mass spectrometer. So you kind of ignore the y-axis on that, but you'll see that as you're increasing the cracker temperature, you'll get some counts, and that'll increase as you are increasing the cracker temperature. And that's sort of expected, right? Because as you're making it hotter and you're allowing gas to flow through, more of those molecules are having the chance to crack apart. And so you can turn that into this plot here. There's a relationship between the power of the cracker and the temperature that it's supplying. So that's just an equation. So you can convert that. And if you find an equilibration point and extrapolate some mean value of counts for that m/z of 1 atomic signal, then you can get these data points here. So that's the y value here. And yeah, so this plot has all the features that we expect. We expect to see cracking start somewhere above 1500, which is quite nice. You can start seeing that we're increasing the mass 1 signal. And if we had a cracker that went beyond 2500, we would continue to see the signal increasing until we'd be cracking all of the molecules in there. And then at that point, you would see it begin to plateau. So this would make a bit of like a sigmoid shape. Unfortunately, we can't get our cracker to get hotter. This is just the maximum temperature it's allowed to run at, but we're communicating right now with the cracker manufacturer to see what can be done about that. And that's really exciting because it shows that, well, to first order, we can do what we wanted to do, and now we can move on to changing some of the settings and trying to optimize and increase the efficiency of things, because in the end, we really want to get as many tritium atoms through as possible and make sure that they have the least chance possible of recombining. We want to keep the tritium as it is an atom. Okay, so that's already my summary. So I talked about neutrino mass scales from the KATRIN and the Project8 point of view. I showed you that the current best limits are set by the KATRIN experiment here, and there's a bit of a historical plot here on the right to show you, to orient you in what the history of the values were in the past for the best fit neutrino mass value. And it's continuing to gather data even now. That's great. The next generation Project8 has some first preliminary results for the small scale. We're continuing to design and construct the next phase of the experiment, which is quite exciting. It's, again, a completely different existence from my KATRIN experimental lifetime, and I'm personally helping develop that atomic source at the Mainz setup. Thank you.
Thank you very much, Larisa, for this very clear and interesting presentation. I would say it's simple great. After so many years, you just restored our trust in mass. That mass score should be not negative.
Yes.
We were feeling discomfort. We were feeling discomfort for a long time that the Mainz and Troyes experiment presenting negative mass score difference. So in this context, I would like to ask you, it is due just to new way of you elaborate the data, or what are the other approaches which were used before, or what would happen you apply your approach for the Mainz, all the data, what you would get, and how your results depend on the energy scale, energy interval you are considering in this analysis, how stable it is. And once you have positive mass score difference, I think it's time already to give even some constraint on the density of relic neutrinos. As we know, there are 340 in 1 centimeter square. We expect, nobody measured it, there is no technology for it. But do some clustering in the central galaxies or so, it can be the density much higher. But nobody till now give any constraint on this quantity. Could you do it?
Probably. Actually, I'm glad you mentioned relic neutrinos, because there is a subgroup within KATRIN that specifically tries to address this problem, and we're actually internally preparing a paper for that. So in some amount of time, keep an eye out for that. Yeah, but I'm not personally part of that effort, so I can't speak about that.
And congratulations to your Nature paper. This result is it. And please, also I have to stress that really this subject of the atomic principle is very important.
Yes.
To exclude many systematics or all this vibration of the molecular rotation and so on. So please, other questions.
Larisa, first of all, thank you very much for a really clear and instructive for us talk. Also, it was clear also for people, for non-neutrino people, I would say. I will start with what Fedor said, relic neutrinos. At the beginning of your talk, you mentioned that one of possibilities how to measure the mass of neutrino is cosmic microwave background. This cosmic microwave microwave background is somehow influenced by relic neutrinos or what? It was not clear for me.
Yeah, that's a good question. This is really this cosmic microwave background approach to neutrino mass is really something that is more of a cosmology question. So the cosmologists would be better equipped to answer it. However, I do have to say that I do know some things. Firstly, that the disadvantage to that is that you are extremely dependent on your model. You really need to. I don't know, when I see my friends who work on this kind of thing, they say, oh, we have a bank of so many different models, and your answer can really depend on which model you pick. So it depends on the model. And the other feature is that it can't actually tell you what a single neutrino mass or effective neutrino mass is. It can only tell you what the sum of M1, M2, and M3 are. So that's just a feature of how it's calculated. I don't personally know how they calculate these things, but that is my rough understanding of how that particular approach works.
It is some effective mass.
Yes, well, in the case of the CMB, it's not an effective mass. It's the sum of M1, M2, and M3.
It's not the sum, okay.
Yeah, yeah.
Then the second question, can you go to your result? Excellent result, congratulations to this result. I was on iChop conference 2020, and there was a KATRIN experiment result. It was 90% confidence level was, it seems to me, 1.1, and the mean value was negative.
Yes, that's correct.
Highly negative, no, highly.
That's correct, yes.
Was negative. In this case, you have the uncertainty point 34. Mm-hmm. It's practically only systematic uncertainty, or statistics also play.
I believe this is our entire error budget. This includes the statistics and the systematics. I can flip to a systematics error table of errors if you'd like.
Okay, if it is possible.
Yeah, it's somewhere in my extra slides. There we go. That's our systematic budget for that paper. So as I said, this is the 0.34 number, and this is the statistical.
So still statistically
yeah.
dominated.
Yeah, okay. Actually, this is a good point to make. When we first designed the KATRIN experiment, we had to say, okay, how long do we want to run? Because funding wants to know how long this thing goes, right? It was determined that we can, that we would get the most bang for our buck if we chose to measure until the statistical and the systematic uncertainties were the same. So it made approximately the same contributions. That makes sense because after that point, measuring longer isn't going to get you very much increase in sensitivity on your neutrino mass. But so we're planning to measure for a total of 5 calendar years. So that's about 1,000 days of total running. And right now, I think we are closing in on having accumulated almost a third of our entire data set. So that's as of right now. What I'm showing here is a smaller data set.
But a possibility to improve your result is...
Exactly, yeah. Yeah, and if we continue to improve on our systematics, and that'll likely be the case because we have a few years, can get even better.
And if I can ask you to go to slide one, probably the last question, my last question, to slide 11. You measure this formula for effective neutrino mass. Mm-hmm. It's very interesting because we know what is the difference between mass operator eigenstates between first and the second, first and third. So if we suppose that the lightest neutrino has 0 mass, then we can find what should be the minimal value of this effective mass, yes?
Right, because you can determine at least one,
yes,
one of these,
yeah. But you have these elements of oscillation matrix, not? Mm-hmm. So if I know that, if I suppose that the lightest neutrino has 0 mass, then I can then I can, using the differences between masses, I can find what is the minimal effective mass for electron neutrino. Am I right or not?
Yeah, you could. I believe you can. So what he's referring to, these nuclear matrix elements, are actually just some product of sines and cosines of mixing angles, and then on occasion some CP violating phase. So you can, and we get those values from oscillation experiments, which is a different kind of neutrino physics. So you can, I believe, actually calculate these, like plug it into your calculator and get a number, right? So you could do that, but again, you would be assuming a lot by saying the lowest neutrino mass is 0, which might not be true. We don't know, but you could just say it, crank the numbers, and say yes.
I want to say that measuring this effective mass, you are measuring at the same time the M1, M2, and M3.
Yes.
Sum of squares of these masses. Yes, am I right?
Yes.
So my feeling, maybe I do not understand correctly what is how it is done, but in this case, it seems to me that in principle you can calculate what is the minimal effective mass of electron neutrino, just using differences between masses and the fact that you know elements of the Japanese metrics.
But she told it already that you need some additional information. You have two mass for differences, but you would like to know the spectrum. You need additional information for beta decay experiment, like she's doing, but doctors of beta decay or just cosmology. So then you have it. Yes.
Okay, but all these elements are known. I would say, if I suppose that, let us say, the lightest neutrino has 0 mass. Okay, no, but in principle, I can calculate this.
In principle, of course, you can do anything. Yes.
Okay. I will have possibility to give.
Yes, let's give.
Yeah. Maybe we can talk offline. Yes. It's a good question, though.
Please, Amina.
Hi. Thanks for such a nice talk. So my question is from CMB cosmological measurement, we know that the sum of neutrino masses should be less than 0.12 eV. So my question is that if the mass of neutrino is really 0.1 eV, then how long KATRIN would take to reach to that label, to that mass label, like 0.1 eV?
So your question is, how long would KATRIN need to measure in order to have a sensitivity of 0.1 eV? So that's half of the sensitivity that it has right now.
Exactly.
That is a good question. I think it's quite long, like more than years. Maybe I can't give you a talk. There's a specific number. There is a plot, but it's longer than any reasonable funding agency would have the patience to give you.
So actually, my question was whether, like, the current setting that KATRIN has.
Yes.
So can that approach to that level of precision, whether the statistical uncertainty would not, like, the systematic uncertainty will be larger than the statistical. Like you can't reach to that level, even though if you have larger statistics, because the systematic uncertainty is not that good.
Right, you're fighting. The two are fighting. I mean, you have to have the statistical, which is just more measurement time. And then you have the systematic, which is something you do have a little bit of control over. You can just do more work in characterizing your system, in trying to be very clever about choosing your settings. In fact, there's a few things we've already done right now, implemented, which are completely new. They were not on the plan, on the schedule for when this was designed, that have tried to, sort of cheat away at the systematic budget. I mean, one example I can think of is, let this be too difficult. We shifted the magnetic field settings in the spectrometers such that the electrons that were guided through that spectrometer took up a smaller volume. And so because they took up a smaller volume in that, there's less chance that there will be some interactions that create secondary electrons, which are not actually tritium. So there are like little things like this that you can used to try to improve sometimes your systematics, sometimes your statistics. But at the moment, I'm a little bit pessimistic that we'll get to 0.1 because the 0.2 is already quite good. Yeah, no, good question.
Result, I have to say that cosmological measurements are very model dependent.
Yes, that's also the selling point. KATRIN, although I showed you a model, like the physics model, it's not technically a model dependent because you don't just pull out your stack of of physics models and say, okay, apply them all. Yeah, I mean the model's really grounded in, I would say, a lot of nuclear physics and stuff. So.
Some other questions? I think you would like to comment or
let me ask with regard to project.
Please.
With regard to Project 8, which you're now working on, it promises to do rather better.
Yes.
Better than KATRIN ever could do.
Yes.
Why is it that this particular method has this much greater promise? What's the fundamental difference that allows it to be so much better?
That's a good question. I've already spilled the beans on part of it. One part is switching from molecular tritium, which is what KATRIN uses, to atomic tritium. That already gets you pretty far. The other thing that I want to point out is that it's a frequency-based measurement, and our ability to do frequency-based measurements to very high precision is actually quite good. The technology is there. Some famous physicist whose name I don't remember said, if you measure anything, measure frequency. And so that's really part of our ability to get to very precise values. So those are the two biggest components that I can think of right now.
And then, are there other projects or approaches in the planning stages or developmental stages that can do as well as Project 8 has the potential to do?
Let me think. So when I list kinematic methods, let's just pretend I'm only talking about kinematic methods. These are methods that use tritium, or they look at holmium or something like this. That's another isotope you can look at. I mentioned electromagnetic collimation. Right now, KATRIN is the best precision for that one. Sorry, sensitivity. The frequency-based measurement, Project 8 really is the only game in that town, so they're really, the top for that category. A third category that I didn't mention is you use cryobolometers, so you try to measure very, very small changes in temperature inside some material, and that can also give you some information about the kinetic energy of beta decay electrons. I think that usually uses holmium or something like this, but Echo, Holmes, those use holmium.
But how can something that's measuring temperature ever compete with something where you're measuring a frequency?
That is a good question. So I only know a little bit about this cryobolometer stuff. It's really interesting. They started implementing some new solid state methods. I think they're using squids now. Basically what they're doing is they're using these devices to measure changes in inductance, and through that you can get somehow a change in temperature, and through that you can find out some information. Ask a Holmes, an Echo person. But I don't know what their sensitivity is. I do know that it's certainly still fair game. I don't know whether it's closer to KATRIN or to Project 8.
I cannot see other questions. If there is some urgent, you can still stand. I know that just one sentence. But for you would like to say? Okay, I will give you a chance because then you will say,
I want to say that if we can go once again to slide 11. Yes.
Yes.
If I correctly understand, it means that at act of decay is created, in the case of tritium decay, it is created neutrino Ni1, Ni2, Ni2, or Ni3. In such a way, in principle, all three masses could be measured by measuring the spectrum of tritium, if
Yes.
you have very precise.
Exactly. Yes.
So okay.
Yes, that is exactly right. Let me make it clear to everyone else what we're talking about. Let me find a nice. Okay, so what he was saying was, if let's say the KATRIN experiment suddenly found a new way to make its measurements much more high resolution than 1 eV. Let's say it got 1,000,000 times better. So what you would do at that point is you would measure this endpoint again, and you would measure it at very fine points. So you'd measure a lot of points here, right? If you had a sufficiently high resolution, then you would see actually bumps in this endpoint spectrum where it looks like someone has added one tritium spectrum on top of the other, but each tritium spectrum has a slightly different mass associated with it. And so if you did have sufficiently high resolution, you could do that. Unfortunately, I think it's way beyond what KATRIN can do. Already 1 eV resolution is crazy in our field. I mean, but this actually brings up another small tangential point. The idea of having these spectra stacked on top of each other for different neutrino masses is a way that the KATRIN experiment might be able to say something about sterile neutrinos. And that is an idea that there's a fourth mass eigenstate that you can oscillate into that doesn't interact with matter, and that's why it's called sterile. And so the KATRIN experiment in its second life after it's done looking for this problem will also be scanning the rest of the spectrum a bit further up for evidence of this kink structure of where one spectrum is stacked on top of the other. And if you find that kink, then you can say, aha, if I fit that, I can tell you what the mass squared value is for that, and that'll be the evidence of the sterile neutrino at that particular energy. But yeah, that's a completely different topic that I'm not going to go over very much else on.
I would like to thank Larisa. Thank you very much.
Thank you. Thank you.